Yeah, it's in Greek. Yeah. 48 side. 14. No. This is 48 by 1. What is it? It's oh, okay. It's definitely So, I mean, so let's see, like the full installer image, which is actually a superset of the operating system, is like 40 megs. And then when you install it, and you do this as a OFS trip, so it actually only uses RAM or anything you want to do. But the image actually stays static on the disk. So we actually think this is a feature. So it's not like a normal operating system. Anytime you're doing it, just lose everything, which I think is the right thing for us. There's actually this debate as to whether we want to have a mode and I think the answer is if you wanted to tinker around with stuff, or if you wanted to make your system all the time. Well, but that's the thing is love service, right? You hope they look at that. Depends on what you're watching.
The problem is, like, a lot of servers
That's true. Yeah.
Something bad is on
There's generally cable lasts. The good news is, like, all of these things are very, like, trivially possible. This built on this is this notion of what we call a switch image. They go really work together. Version information, and then we're both in the box image. So the Windows map is shipped around as a read-only binary, or unpackaged and exposed through NFS, or unpackaged directly on the disk. You can do all of these things. Yeah. Distributed work. So that's actually how we do upgrades. So for our commercial product, we use all the same stuff. We have built actually all the technology is there. It can pull off a centralized controller, which is CHCP. Tell you what the version should have, and that's what it would control the hash. There's the cache. It doesn't have any grounds. But actually, so there's like these different processes. So that process happens in our bootloader, which is different from how we actually don't go through it. And so by having our own bootloader, it lets us do some extensions on top of it. So we can now do like an NFS-based route, or we can pull from SCP. So it's just, I've got a little slide where it's like, Pony is like a 3 meg install. So our bootloader is like a 30 meg install, and Switchlight's like a 100 meg. So it's a question of like, how much stuff do you want for an operating system? Like any operating system, you have the whole stage process. Oh, they did, yeah. I think it's what we were saying earlier. I think this is mostly useful in getting all the people together going to one word, saying exactly what we're going to download right now. They do work as notifications, but it's not as smoothed over and productized side like those strange rare interfaces. So we have, I mean, the way our commercial products work, we actually engineer for qualities to make sure it's one issue. But at the same time, I mean, you know, we talked through it a whole bunch. This fast reload of like the user space agent, in which case you might just cache everything locally. But then there's stuff so if I go down that route, I would actually probably go more the Linux container more Vent but it's clear that our code process is not optimized by having some change in the process. That adds latency.
No, I sent the mail. I sent the mail too.
He's right there.
Oh. All right. We've got a few minutes. We're going to start off in 3 minutes.
She's thinking whether I want to. Yeah, this is how the special sauce works. Those are Good scene. Good scene. Jump up and down for you. Last night. Here's the hard question for business. I flew out to Australia and at the last second we're getting a 15-hour flight. I got upgraded like the last second. I was pathetic. Like, hey.
Is it gone? Carlos. Oh, you made it. How'd you sneak in?
I didn't have to. Did you know that basically after lunch it's now open? We could have said something about that, but basically, so when I showed up, I said, hey, you know what? Oh, we're letting everybody know. I think this morning the problem was that they just didn't have a lot of space for the show. And they didn't want
That's
to
just like a complete. This is a Charlie Foxtrot. That's what it is. Whatever.
I don't want to.
Yeah.
What does that mean about it? But you,
No, I.
it is that
Yeah.
they could have said no. Show up after
Okay, cool.
Okay, let's get started. So we've got Rob Sherwood from Big Switch to talk about Open Network Linux. Any logistics? Brandon, like I did.
No, you're good. You're good. I'm trying to think. We're good on the IRC. Participation. Rob, hey Rob, you might want to take off your lanyard.
Actually, I think this is actually super high gain. I didn't want to switch off for that. Or is this really? I'm hearing also what's that. How are you guys?
You sound great.
Yeah.
let's try that again. All right. Thank you everybody for having me. Who has heard of Open Network Linux before? Really? I'm done. Drop the microphone. Apologies in advance. They asked me, do you care if you talk on Monday or Tuesday or Wednesday? I was like, what do I care? I talk about this stuff all the time. Apparently all the press releases are coming out tomorrow. So all the stuff that I think is really cool, I can't talk about. So think of, check the mailing list. I'll have a bunch of announcements that pop up tomorrow. In the meantime, I do have fun things to talk about. And since everybody's heard this before, I'll probably whip through some of the preliminaries pretty quickly. I'll talk about what is Open Network Linux very briefly. It'll give you my view of what a network OS architecture looks like. I'll whip through some of the things that ONL provides. I'll talk about plans for the future and how to get involved in case anybody's actually interested in contributing to this. I usually start with what I think is a background slide. How many people think networking is already open? Really? I love this audience. So, depending on what hardware you use, network can actually be really open or really closed. If you think that networking is based off the x86 servers, which, there's actually, host networking is a real thing. There's lots of useful things to do with it. There's lots of people who are doing interesting things with vSwitches. That's really, really open, by which I mean there are, all the hardware specs are public. You can download the Intel docs and do lots of interesting things. If you follow a continuum through network processors and FPGAs to single-use data center boxes like what we've got up here to multi-chassis routers, you kind of see this trend of the faster it goes, the more closed it is. And so really what I'm talking about for this talk is taking this one little piece so far and making this a little bit more open, by which I mean moving it from you can't get onto the operating system, you can't get to the control plane APIs, to you can get to them, but those SDKs might still be binary, which that's progress. Is it as good as we have for x86? No. Is it progress? Yes. So, completely different way of looking at this. If you're at all interested in FTN, there's lots and lots of controllers in the world. That's very cool. There is only one operating system that I know of that is open source right now that you can actually get an OpenFlow agent on and not put this in. It's another different way of looking at this. So what is Open Network Linux? Open Network Linux is a collection of software packages, utilities, drivers, APIs, abstractions, trying to get Linux or some fraction thereof to run on all the switches. In other words, it would be a DOS that only installs, or an example DOS. So why not use an existing Linux distribution? Well, WWDC does almost all the hard work for us to build on top of that. That said, you do need to actually wrap up your packaging to work with only in a certain way. There's a hardware abstraction that happens there on our side. There's a bunch of specific hardware pieces that don't have analogs in the PC world. Although I could talk about that next with the APD talk. And as much as we like to think that switches can be very similar to servers, they are in a lot of ways what they aren't to others, particularly in terms of what hardware they ship with. If you think you can treat your compact flash just like an SSD, you can't. So there are tricks that we do to manage that as well. By the way, any questions? I'm talking about this quickly because I assume you guys know all about this, but if I'm going too fast or just want to give me a hard time, that's fine too. The target use cases of this are, I was a grad student for a long time. I was really annoyed that I couldn't actually come up with my own routing protocol. So if you are a DIY, do-it-yourselfer type person, like a grad student or a hobbyist or what have you, the barrier to entry for just working on these boxes is too high without somebody else having the fan drivers, some of the base packet forwarding drivers, some of the stuff that you need with to get ONI to actually hand off to the NOS to install properly. All that is effectively useless to you, and this is just to help get this started for you. My hope is this also is an open reference hardware testing platform. And last, and this is where at least with my commercial hat comes in, you can imagine this as part of a building block towards a larger commercial operating system. And my friends from Peak 8 are here. I saw Olivier somewhere. There are other people thinking along the same lines too. So why use ONL? I'll just skip this. What does a network operating system look like? So a generic network operating system, if you think of the hardware, there's, at least on boxes like these, there's a physically independent CPU. There's a bunch of miscellaneous hardware. By the way, the ONL slide template completely destroyed both the colors and my fonts of all these things, so apologies in advance that some of these things are too small to read. There's a bunch of miscellaneous hardware like fans and LEDs and SFPs, and then there's typically one or more packet forwarding ASICs. On top of that, you might run an operating system, something a lot like Linux. You might have a SDK for that ASIC. Ideally, you have some sort of platform abstraction layer on top of that, and then you might have what I call a bunch of applications. So either environmental agents, things that tell you how fast the fans are running, or things that actually decide how your packets are forwarded. So maybe a traditional L2, L3 stack. This is roughly what I think of as a generic NOS. So when you get ONL right now, what you get is a Linux kernel, so it's Linux and a bunch of additional drivers. You get a closed source instance, the Broadcom SDK. You get the ONL platform abstraction layer, so which means if you want to write an application to monitor how fast the fans are spinning, when there's an SFP plugged in to get events from that, you actually do that in an abstract way that is independent of the underlying hardware. So I'll talk about what hardware platforms we support in a bit, but there are 10 plus platforms we support, and they all do this differently. But your application doesn't have to worry about it if you use ONL. It ships with a thing that runs the fans, a thing that lets you query the system to tell all the different components about it. It ships with SNMP drivers so that you can actually monitor this remotely. In case you want to get SNMP traps or your box is overheating, that's how these things get implemented. And it ships with a piece of code that I even generously call like a hello world piece of code. It's called the Open Route Cache. It is not terribly good. It's not terribly well implemented, but it is a basic L3 stack to take routing events from something like Quagga or Zorb and just sync the software routing table into the hardware routing table to enable some basic routing. Should you deploy this? No. This is about 2,000 lines of code I wrote while I was on an airplane, but it's to give you an example of what an example forwarding driver for how to forward packets in this world. In the next couple of days, we'll be having some announcements with other companies here about doing more interesting things on top of this, but this is what ships when you get ONL out of the box right now. Questions so far? As a side point, the Bork Broadcom driver, and by the way, I have Broadcom listed here because that's just the code that I've written. There's lots of extensible drivers here, so I'd like to extend this to other ASICs. If you have other ASICs you want to work with, talk with me, or even better yet, if you work with an ASIC manufacturer and like to work in this stack, I'd like to work with you. Sir, you had a question?
Just wait. Just wait.
The question was about LXE support? Yes.
Yes.
So, the question is, do we support Linux containers, LXC? Yes. So the kernels that we compile have support for Linux containers. We don't actually use them at all, but it's a Linux operating system. You can get a shell. You can create them on the fly. We don't do anything to prevent or to enable them, which it should work. Yes. I can just repeat the question, Carlos. So the question was, am I considering moving ONL to Psi? Let me dissect that question, if you will. So this particular API here, between the purple and the green, this actually looks a lot like Psi, and I created this about a year and a half ago now. Moving that layer to Psi, I think would make a lot of sense. ONL is the whole picture. Okay. Yes. So assuming that Psi gets adopted and I can actually use it, which it seems like that should be the case, it should be very easy to drop in something else here. So you can imagine the org Psi driver. Yes, that is my intent. Here is an abbreviated list of companies that work with ONL. If your company is not on this list and you do work with ONL, I apologize in advance. My laptop died and a lot of these slides are reused quickly. If you talk to me afterwards, I'll make sure to get your name up here. I won't go through this in detail, but if you think making a distribution is not hard, it is. This is kind of a visual diagram of what it takes to end up with the end ONL ONI installer. So we take a bunch of kernel patches, we patch a couple different kernels, we build a whole bunch of daemons, we have this whole BusyBox-based loader. All of these things get built into Debian packages, which then with a whole bunch of other packages from Debian.org get built into a switch image. We wrap that with a self-extracting archive wrapper, and that ends up with your ONL ONI installer. And so when you actually download the binary from the website, you get the thing on the right. If you actually want to build it, you actually get all of this process done for you automatically. People also ask me, how does this compare to ONI? Because ONI is in its own way a standalone operating system. I think the graphical picture makes the most sense. So ONI is a one-time installer. You can think of it as a better Pixie boot. During the normal course of the operating system, it is actually not run. After you've installed an operating system, it's not even run typically. And it's actually stripped down very intelligently to be very small. It's still about 3 megabytes per. I'm talking here.
Yeah, it depends on the CPU architecture. It's around.
Okay. So there's been some code bloat, you're saying?
Yes. And also the GitHub URL is opencompute now.
This slide is very old, and I apologize for that. I'll have to change that. Thank you. But so, my point being is, ONI is intentionally stripped down to be small. We have an intermediary stage bootloader, which has some more utilities added to it, and then the main ONI image is actually supposed to be kind of a development environment, so it has full-featured binaries. It has the ability to add more stuff. And all three of these things, in my mind, have their own individual uses. We have been talking about refactoring the kernels to actually benefit from the same common stuff. It remains a good idea. We'll eventually get around to it. ONL's been around for about a year. We've had more than 6 different platforms contributed by the community. I think that number is up to like 8 or 9 now. Code contributions from many different companies. I will just skip through all of this. I think most people either know this or don't care. We support over 10 different platforms right now. There are 2 other platforms that I'll talk about later that are being contributed by other companies. Just briefly about how ORC, the Open Route Cache, works. It queries the underlying SDK to create Linux interfaces for as many front panel ports as you have. Those show up as an ORC like 05 interface. You can run a native dynamic routing protocol stack like Clogger or Zork or Bird or what have you on that kernel, pointing them at those interfaces. It receives RT-Netlink updates. And then given those updates, it actually does the appropriate hardware calls to mirror that state from the software stack into the routing stack, into the hardware SDK. It's very limited. It only does IPv4 now. It does no IPv6, no multicast, no ECMP. As I move to SCI, I can imagine expanding these things. Is that your question? Let me try to paraphrase that for folks who are remote. There is a switch device API being created out of the NetDev group, correct? And what is my thought about this approach versus the switch device approach? Is that a fair approximation of your question? Yeah.
Or all the applications limits are hardware, and then subscribers should on the hardware. Those subscribers are you are short one, and wondering together. I'm not saying which is
Yeah.
better or if there is better, but it has roadmap.
So let me clarify ONL versus the Open Route Cache. So this is a user space daemon that runs on top of ONL. So ONL, the platform, could support both approaches. In terms of which approach is better, I actually had a great technical conversation with this before the break. It comes down to, in my mind, do you think that the Linux kernel is the right slow path for your router? If you think that Linux kernel is the right slow path for your router, then the kernel-based NetDev approach, I think, makes the most sense. If you're looking to have your hardware router have different functionality in the slow path than the Linux kernel does, which there are reasons to do that, and a lot of commercial implementations actually do that, then it does make sense to have decoupled version. I will say the only reason I did this is this was easier. I think the NetDev folks are really smart, and they'll come up with a great interface. It just didn't exist when I was doing this. Other questions? One of the things that's most useful at ONL is it has a platform abstraction layer. If you think of SFPs, a lot like USB, they have a whole life cycle. If you plug it in, there's an event that dynamically happens. Different things in the operating system interact with that. There's a query mechanism for understanding what the SFP is capable of. You have front to back and back to front power supplies, and they're hot pluggable, all sorts of throughs. Not all the platforms have BIOSes. Some things actually do some very strange things under the covers. To have your application decoupled from the hardware pathologies that are underneath it is actually pretty valuable. So we provide an API for doing that. In theory, the API is not even tied to a Linux subsystem, although in practice, all the implementations are. If folks want to know more about this, feel free to grab me. Ideally, this is an implementation detail. Unless you're writing one of these packet forwarding daemons, you don't have to worry about. I don't think this slide has actually even changed since last time I gave an engineering update. I'm happy to fill this out. I'm actually trying to be sensitive to time because I was told there's some more talks we might try to slip in. So I'm skipping ahead broadly for things that I don't think that the larger audience knows about. Already? Oh, well, I'll go back. No, I'm kidding. So there are a couple things, and this is actually not even true for the newest switches, but certainly for the switches that ONL is trying to support, where they're not quite server-like, meaning that they don't have spinning disks, they don't have a lot of RAM. And so one of the ways that we solve this, so this creates a couple different problems. One is Flash has a maximum cycle time. You can only write to a certain block a certain number of times before it decides to stop accepting writes. This is kind of suboptimal. And the other is they typically don't have as much RAM as a modern server. And so one solution to this is actually we have this feature we call overlay FS. It's a kernel patch. What happens is the disk image is actually read-only. But what happens is that disk image is copied into a RAM system, a RAM disk, in a copy-on-write fashion, meaning that the entire file system looks like it's writable, but it's not stored into RAM. Only once you edit a file is that copy copied into RAM. And then any changes that you have to the system intentionally get lost when you reboot. Depending on your worldview, this sounds eminently sensible because you run large data centers and you want these to be stateless devices, or this sounds crazy because you're trying to do DIY work and you want to install GDP and Valgrind and all sorts of things, and you don't have to do that every time. The Open Network Linux was created for the people with the first mindset, but there seems to be enough interest on the mailing list for the second mindset to actually have this as the development environment that we're probably going to create some sort of option or flag to the installer so you can have both. It's actually pretty easy to convert from one to the other, but pretty easy for me because I know all the shell commands might not be pretty easy for you. So, but given that we do this overlay FS trick, that's the top half of the slide, we can actually get away with using full-featured binaries. But that is, the real honest-to-God Debian binaries that you would know and love that you would like to use if you're using your own development environment. For example, if you want to run configure from your favorite GNU compatible source code, that probably will not work if you have a BusyBox-based file system. Because we do this overlay FS trick, we can actually have full-featured binaries. Questions on this? We do have a second stage bootloader. It is useful to have a bootloader that runs every time. Oni is great. Big fan of Oni. It only runs when you install your operating system. And so having a second stage bootloader enables you to do tricks like have a permanently NFS mounted file system, lets you initialize the front panel ports and maybe boot off of the actual physical front panel ports. It just gives us a little bit more flexibility. Whether this continues to exist long term or not, we'll have to see. So probably the most interesting part of the talk, plans for the future. Good folks from Interface Masters have contributed a patch for their Niagara platform. So in the process of incorporating that, that's cool. The same with the good folks from Quantum for their LY6. Both of them have committed all of the Oni installer stubs, but not the platform APIs. So we're going to continue to work with them to flesh out those distributions, as well as doing the testing of it. At Big Switch, we have support for a bunch of the Dell platforms. Those exist in our private repository of ONL, and those will get pushed out to the public in, I think, I was told this week. So that'll be good. And we actually have verbal commitments from almost all of the ODMs and OCP to support ONL. And so that's cool. I didn't know what I was allowed to announce from anyone, so I didn't want to do that. But yeah, the point is largely that there's critical mass around here. And so for any device that's going to be, it's going to be going forward for any device that's in OCP, the target will be to have ONL ported to it. One of the things that's cool, I apologize, I've actually had a version of this slide for a while now. We're in the final throes of getting it approved with various lawyers, but the idea is actually just to be able to run an OpenFlow agent on ONL. All the code is written. I can show you demos if you're interested of our Indigo OpenFlow agent with an OFDPA driver. How many people know about OFDPA? Yeah, about half of you. So OFDPA is Broadcom's attempt at a OpenFlow-friendly API. It is closed source but open API, meaning that I can actually publish the code that's built on top of it, even if I can only ship OFDPA itself in a binary form. There's a bunch of people interested in this. My hope is to get this out in the next month or so. We'll see what happens. But so this is also on the radar. Maybe most notable at OFDPA is it actually describes a hardware pipeline that looks close to what the physical hardware pipeline is. And so if folks are curious about how to program for something like this, there's reasonable documentation for it, unlike other OpenFlow implementations that I've heard and seen about. So trying to wrap this up, if you're interested in this, if you think this is cool, join the mailing list, try to compile the code, think about porting a new platform if that's your cup of tea. Apologies in advance, it's becoming almost a catchphrase, but I really do believe that feedback is fine, but patches are preferred. And so if you have great ideas for where to take ONL, again, the feedback is fine, but we'd really rather have the code. There's growing support for this for both OCP and non-OCP switches, and we're going to continue to build out documentation, binaries, and example applications on top. If you guys haven't had a chance to ask any other questions, happy to take more of them now.
Databases. Question is, your framework database some process already when this updates that is over something
So first, let me try to recap the question for people who didn't have a microphone. So you're looking for databases for switch state that get exposed through SNMP, and you're asking if these are on the roadmap. Is that fair?
this is like the end in mind.
Yes. Someone give him a microphone. I'm not going to be able to summarize this. You are a wonderful, eloquently speaker, and I don't want to take away from that by trying to summarize what you're saying.
So what I'm saying is basically I'm trying to look at high-level vision of the ONL as a framework of building an operating system to manage switches, right? So we have a sort of how to accelerate the hardware. We have a sort of how to manage the switches. We have interfaces in the outer world like OpenFlow or SMP, and you have shown integration with protocol stacks, right? There is an operating system, and there is a way to work either kernel or user. We talked about it before. And the piece that I'm missing, at least in the vision, is a database. Normally, when you want to build a switch system or any system, you need to have a database that this user can go configure it, save its configuration to a disk, then boot it up again, and be able to have multiple processes signal each other. And well, there are frameworks, not too much open source, but there are frameworks of creating databases for management systems. Normally, this is a major part of the NOS when you're building one, and I see. I'm quite lacking this, at least on the charter where we want to go. And the question is it planned, or this is something that's skipped, or this is something that you're...
So I guess a couple of thoughts. One is very familiar with the databases you're talking about. You're talking about some sort of centralized state store. I will say that store is typically tightly coupled to the applications that run. The way you do that store for the OpenFlow agent versus org, just to have two things to point at, is completely different. And so, at least in both of those cases, that state is actually stored internal to that application. Who took his microphone?
Get it back!
Yeah, I don't like
It's a good question, by the way. I mean,
so you're right. It's a matter of application. But for example, it doesn't matter if I'm using Berg, Quagga, or SORT. I'm still creating my loopback interfaces or my router ports or my 4K VLANs, and I need and sometime afterwards, a remote management or an NMS can query the MIPS that describes them, those IF MIPS, etc. And I still need a database that can be able to cache it and show it. So you're right, it's protocol dependent, but still, even if there are many protocols and different implementation, I still need a centralized database that has the same scheme, same language.
Maybe it's worth pointing out the SNMP daemon that we use. It's a NetSMTP. Actually has all sorts of pluggable modules. And what we've seen, at least in our commercial implementations, is you start with this. We have a couple modules already for the platform abstraction layer, so you can read the fans and whatnot. But you're right, that's not all the state you'd like to expose. And so what ends up happening is, for an application, you would probably also have an SNMP pluggable module that pointed to whatever your application-specific database was. So if you choose to expose VLANs or not, or OpenFlow flow tables or whatever the right thing is there, there's extensible mechanisms in this picture to make that happen. If you were leaning towards, let's create a master database in ONL that works for all applications, or at least a subset of applications, I think that's an interesting technical challenge. It's not one that I'm even positive would actually work out long term. So,
I must remind you that as a community, we have been challenging the ability to have one language describing silicon interfaces and size around the corner, or it's already there. As a community, we have challenged the ability to describe as a language how the hardware, the system platform can be represented. Cumulus are going to represent the system, and I think that this might be a very interesting charter for us as a community to try to define switching software, a language, a generic language that defines what are the databases it requires in switching software, and then have anyone plug his own application on top of it and build an ecosystem with multiple applications, as long as they're talking to a single database. Is my vision.
Yeah, it's a really good too. It's an interesting piece. I mean, open network Linux. I think you've got a bunch of the pieces on here, but you're absolutely right. For the community, like if we wanted to do, we've started our software kind of at the bottom layer, right? At the SDK layer, the shim, the SI, the operating system installer, loader, right? As a group, we haven't. I just got a question from somebody else, like, hey, what about applications for traffic engineering? I heard that from the lecture. Right? What about an application for configuration management and automation, orchestration? What about distributed state replication, kind of a little bit lower? What about state sync, some persistent storage? So those are higher layer software packages that I don't think is grappled with yet. But I think it's just a show of hands. Like, who would be? I think like I said, we've started low, and I think we may have managed to get a lot of progress there. Who would like to start thinking about the next, whether it's state persistence or state syncing, state configuration utilities, orchestration? Who thinks right now we should just actually stick at the low layer hardware? Don't try to go up any higher. The rest of you.
I think that's a tough. I saw 4 versus 3.
The sample sizes. So basically, I saw 4 versus 2, so I was coming away with like double the number of people want to do that. No, but I think just we're not. Like for example, the SAI started. I think we started talking about the SAI way back in January. I think the last.
I presented in OCP.
Yeah.
The OES there, which like something trying to say there can be a generic interface that I think that.
Yeah, the last summit, exactly, not the European summit, the last summit here in San Jose, you all presented that, and I think we were having some discussions around that, but it took a while for the community as a whole to say, like, okay, yeah, let's get a couple of different vendors and operators and people kind of moving toward. So I'm just trying to get a sense here, like, are we ready to jump into state and orchestration and management control applications, or are we maybe a little bit ahead still? Just an open thing for everyone to think about. We don't have to answer it here. But Matthew is going to take a shot at an answer.
Well, I think that, to me, the biggest benefit out of doing all the and having the low-level work done is that you can allow a community of applications to appear that can manipulate optimize stack, which hasn't been possible until now. So I think everything that's been done on the low end had to be done, and that will, and assuming that takes root, I think you're going to see applications like that appear naturally. We're going to throw them out there like open source does, and take advantage of it, because now you've abstracted away. No different than Linux has done for the server, and hopefully get the same effect here. So I think that what we have done so far that enabled it to get there, and so. It's not that, so I do agree that we need to, that there will be a lot of work happening in applications. I just want to make sure that as a community, we still need to get adoption of the bottom layer. And so even though I think that will get really important and it will evolve, we also have to stay focused on making sure that people adopt ONL and SAI and all those components that get involved now. So there's still a bit of pushing left to do there.
Thanks. Any other questions for Rob?
If I could throw out just the last point, I think it would be great to have more code built on top of this. I'd love to see the vision that you're talking about. It's just a question of when and where the code lands. And on that note, thank you very much.
Thanks. All right, so we've got do you have your electrical one? Dustin. Okay, Dustin. Yes, Dustin. So Dustin will talk to us about ACPI platform description. Again, all the slides for today are actually up on the wiki. I sent a link on the mailing list for this, so all the slides are available there if you don't catch them during the presentation. Oh.
You do not see this in the remote participation land. These are, we'll just say these are scabs. These will be disappeared in the next 45 minutes.
Yeah, actually, so I have a live demo at the end, and I want to go ahead and get all the cables connected.
Yeah, so while he's doing that and whatnot, so how's everyone doing? We'll just, kind of distract everyone from this non-union work going on behind me.
Here for us.
All right, if you need to use the head, now's the time. Get some coffee. Long story. Long story on not having a podium. Or having a podium, or whatever it is.
Right. Thanks for waiting for a second. So my name is Dustin Byford. I work at Cumulus Networks. And this is the ACPI platform description, also known as E. So a little history about myself. I ported a bootloader in Linux to my first switch back in 2000. This is it here. I designed all the hardware, wired it up from scratch. It was a lot of fun, but I learned very early that switches have a lot of wires. And then in 2002, I took a job at an embedded Linux company that made little controllers that go inside copiers, things like color correction, rasterizing PostScript, things like that. Then in 2005, I started working for VMware, where I guess I could say I gained a unique appreciation for the PC platform, writing various bits of device simulation and working on graphics and USB and keyboards. And then in 2012, I started working at Cumulus, mostly it's a startup, so everything, but mostly working on putting the new platform. And somehow I became a cable guy. So if you want to talk about optics for 5 after this, let me know. So here's the agenda. To kind of frame the problem, what I want to do is talk about the history of platform bring up at Cumulus, kind of how we started, what we did, how we evolved over time, and then where we want to go with it. And the we in that sentence is actually the whole industry, not just platform bring up. So it's in the name, so there's no spoilers here, but we're going to talk about ACPI as a hardware description protocol, and kind of the history of ACPI, what it was designed for, how it can help. And then we'll talk about what platform bring up might look like after AP. Kind of show how the pipeline looks. And then I have some sample code that we can compare various approaches to, and then I have So I'll start with explaining platform bring up at Cumulus from the beginning. And along the way, you'll probably get a little bit of an idea what it's like to work with Cumulus. So step 0, you take the switch apart, you stare at it for at least 10 minutes. This is called the stare down. And it became a little bit of a Cumulus ritual because in the early days, you kind of needed to establish your dominance over the switch a little bit because you got a long road ahead with you. Because porting a new platform is a lot more complicated back then. So you also want to hook up a remote console and JTAG debugger and like stuff so you can work on it at odd hours all the time. And so by long road ahead, I mean, literally we made no assumptions about what software came on the switch. go grab a JTAG debugger, maybe reverse engineer the existing bootloader. It was a lot of fun. And at first we loved it, the first few times. Matt Peterson, the guy in the red shirt there, likes to joke that our new hire training at this point was to basically jailbreak a switch. Maybe a little bit of an exaggeration, but that's certainly what it seemed like, because we were doing all kinds of crazy things to get our first OS image onto those switches. Guessing passwords, reverse engineering CRC algorithm, running flash debugger. But as you can imagine, this approach didn't scale particularly well. It took one person locked in a room, no air conditioning, kind of a long time to get that first Linux prompt. So we wanted to go faster, more platforms, more customer choice. And that's kind of the genesis of Oni. It was designed to solve this problem. And we contributed that to OCP as well. Oni has seen quite a bit of success. I mean, it has, at this point, broad support from all the hardware and OS vendors. And it's pretty much the standard way you get images onto one switch. So this is great for everyone, but really eliminates most of the work in that step one of the cumulus porting process. So step two, now we have a Linux prompt. There's a whole lot more to the switch than just logging in with SSH. We have to configure the switch function in some way. So here's one of the OCP switches, block diagram. And in addition to the CPU, which is actually a CPU complex, which is quite complicated in itself. It's actually only that little tiny green box in this diagram. You have to configure all this extra hardware on the side to make the box act like a switch. It's done per switch, and then it's now another super time-consuming part of the process. And I'll be concrete about what you're looking at up here. You've got like a switch ASIC in the middle, which has a whole bunch of wires running out to the front panel ports. And switch ASICs are very flexible in how those are mapped. QSFP cages and SFP cages. That's for all kinds of signal integrity kinds of issues. So really no two are the same and quite complicated. There's an I2C tree, like all those little boxes you see up there, a lot of those are I2C devices. There's tons of general purpose I/O to those QSFP cages. Another example of that is like detecting if the power supply is plugged in. And all stuff that the OS needs to know at the end of the day. There's NAND flash, SATA disk, thermal controls, list goes on. Another kind of unique thing with switches is there's tons of LEDs. I know at least one switch that has RGB LED per port. So if you're talking 48 ports, 3 colors, that's a ton of wires that are mapped out to the front in a way that's specified by the hardware manufacturer, hardware designer. So then there's also the CPLD, and this is kind of worth singling out at this point. The CPLD is this software reconfigurable device that can perform all kinds of different hardware functions. It has a firmware, it's typically loaded at the factory, and it's a general purpose logic device. And switches are kind of the glue of the system, connecting various subsystems to the switch ASIC. But there's no standard at all for how those are designed, what they control, what register interface they adhere to. And what that does is it guarantees that they're never the same from switch to switch. And we're actually seeing that even inside the same vendor, they're not the same from switch to switch. So it guarantees that somebody has to write a driver for it. There's no way you can expect a brand new switch platform to become a standard driver for those kinds. You always have to start over. The result of this exercise, this spec encoding process, is you've got a pile of kernel drivers for the custom hardware that's in the box. You've got some platform information that's added to the OS image. And at Cumulus, one of our first attempts at consolidating that information was to put everything down in a Python data structure, try to get some reuse, at least in the process of incorporating this information in OS. And a number of OS vendors have done that. Then there's also a handful of config files, LM sensors, more switch ASIC configuration files, initializing all that GPIO, and pointers to things in the system like the OE processors. Not really a standard place, address, device, I don't know the size of it, to sort of store the code, which every switch OS needs to know, things like the MAC address stuff. So if we didn't go through step 2, you would have a box, it would have a SSH prompt, but no front panel control, no LEDs, all these things in this diagram wouldn't really work. But there's also this kind of extra mapping function. How do you ensure that ETH0 is the front panel management port? How do you tell the user what ETY is the front management console port? How do you make sure that the silk screen on the back of the switch match from span 5 to span 5? So that mapping information is also a result of this process, coding that mapping. So as an analogy, and as an example, there's another OS called openWRT, and it runs on wireless access points, and it's got a ton of built-in information about all the different access points you can buy, and a whole bunch of drivers. That's an example of what I'm talking about. What makes openWRT different than stock Debian, same thing that network operating system different than stock Debian. So openWRT makes access points work just like a NOS would make a white box switch for them. So like in step 1, the OS loading problem, we're finding that it's approached, maybe some room for improvement, looking for ways of making it more efficient, more platforms, more customer choice. And we discovered we kind of have a bunch of things working against this. Everything on that switch main board is pretty much not discoverable with software. There's no program you can write to go figure out what devices are an IT bus. Bus is just inherently unprogrammable. What I mean by that is, there's no standard for a device on the bus what address it might show up. There's no vendor and product ID that you can associate a driver with that piece of hardware. There's nothing like PCI config space or USB device descriptors to give the OS a hint about how to use the device, what it's for, how to control it, things like that. And I mentioned before that switches are all different, often even varying significantly from the main vendor. So every time we get a new switch, a lot of this is starting over. We've made attempts to reuse the code, but I think there's probably still room to make it. The other thing is that we're often receiving engineering samples during the development cycle. So the hardware is changing a little bit underneath us, and sometimes that can cause setbacks. And finally, even if the hardware isn't changing, finding that the hardware specs aren't always complete or accurate the first time we've seen them. You find yourselves iterating often across many time zones over clarifying the spec. And this is just kind of all adding up to this pipeline process of getting a switch onboarded. And if you multiply all these problems by the number of platforms we're starting to support, graph here is a graph of platforms in the cumulus code base over time. I started over on the left-hand side of the graph, and there was just 1 or 2 platforms. See that it's climbed. A couple things about this graph is it kind of looks mostly linear, and maybe that's a little bit of a hint that it's scaling with the number of people we can assign to platform porting. And I think the graph kind of wants to be exponential. Certainly, it seems to be nice that it's exponential numbers that we can be porting to. And I think that would benefit everyone in the industry. Also, the area under the curve. Kind of think of that as the maintenance burden of this platform information database. And as time goes on, that's going to add up as well. So that kind of frames the problem that we'll be talking about at the beginning of the semester of ACPI behind. But to round up this platform bring-up story, I'll go ahead and complete that. So step 3 is test. Once we have a switch working like a switch, we have to test it. AVD has some implications for testing, and so I want to hold off talking about testing now. I'm not mentioning it. But then at the end of this process, step 4, ship a new version of Flex. I mean, even after you've gone through all these steps, you still need a version of the OS to actually get the thing into the customer's hands. Which means that sometimes new platforms hold up networking features you want to reduce. Sometimes features hold up platforms. That's just sort of the nature of it. So trying to alleviate some of that might be a good idea. I think we can do it. So far we've kind of got what we asked for. We have a lot more platforms, but hopefully it gives you that there's a little room for improvement in the process. And the style of platform porting doesn't scale particularly well. And the question is, can we do for the OS what Oni did for the OS installer? Can we make it so it's not so much work to port to new hardware, all work that's been repeated by every OS vendor, unfortunately. And I suspect, like Oni, power is going to be a broad support. It has to be something that the industry can adopt. So how do we attack the problem? At this point, I always think of the homework machine. So at this point in the process, porting is starting to seem like homework. So here's an idea. Let's just take this hardware spec, PDF, and we'll just shove it into this machine, and it'll grind on it for a while and generate my driver config files. That sounds like a good idea, and it's certainly pretty cool. But actually, maybe it's not so far off. What if we made the spec machine readable? Then we can make the machine a lot simpler. And if we put that machine readable spec into the firmware that's shipped from the factory, maybe the OS can load, read this configuration, and from firmware and configure itself accordingly. At least that's the idea. And if you look around, it's not such a crazy idea in operating systems. It's referred to as a platform description protocol. And it's a kind of a contract between hardware vendors and OS vendors about how all this undiscoverable information about the system is coded, made available to the operating system. So it sounds like we need a platform description protocol for all these switch functions. A way for the hardware to provide information about itself directly to the OS. And as long as we're asking for that, what other properties of this? Well, it should be easy for hardware vendors to deal with it. And the point I want to make there is the OS vendors are probably not the right people to write the hardware vendors that know their hardware the best, and they're in the best position to encode the platform description, just like they're in the best position to write the hardware spec. Second thing is it needs to be comprehensive. It needs to describe all of these extra pieces, which if we leave anything out, we're not really realizing the full benefit of it. And maybe that means we don't even have to change the OS to support the platform. Everything's encoded in the platform description. It's possible for the OS to run hardware that is actually in. But how do we get started with this? Well, we could continue with our own description protocol. That's kind of those Python data structures. We thought at first about, let's bake this Python data structure into firmware and do something like this. But you kind of also have to look around at this point and see what else is out there. I mean, those protocols weren't designed to be embedded in firmware, but maybe there's something else that is. And you'll find with a little bit of research that two things pop up, device tree and ACPI. Device tree is definitely one way to do this. It describes all of the hardware in the system, this hierarchical data structure where p-value pairs are associated with each device in the system. It's popular in Spark, Libs, PowerPC, not protocol used on x86. If you look at x86, that's ACPI, which stands for Advanced Configuration Power Interface. It's been used for years to tell OSs about all the things that differ between desktops, laptops, and servers. So, since the trend seems to at least be that a lot of new switches are x86 based, it's definitely a protocol we have to take a really close look at. It wasn't as important a point of the design. So, as fun as it sounds to kind of build the cumulus homework machine into the firmware, not start from scratch and then the ACPI. So I know what you're thinking, ACPI, isn't that the thing that broke my laptop when I closed the lid? And there's tons of horror stories of ACPI. I can't explain them all the way. But, maybe in the early days, you're looking for reasons or rationale for why that happened. I don't think Linux was all that well represented during standards development or the implementation of ACPI. And knowing what I know now about it, I don't think ACPI is a mechanism so much at fault for that. But that's just the best thing I can do for you is cite some examples of where it works. Linux plus ACPI plus some random server pretty much work today. If you look at Windows on laptops, buy a copy of Windows, you kind of expect it to work on a laptop for the most part. And we have some recent examples of how ACPI is being used as a platform description protocol for ARM servers, for Linux ARM servers, in fact. The folks at Linaro are kind of going down that path. So, I don't know, maybe we'll talk a little bit about the origins of ACPI, what it was designed to do, and compare that with what we wanted to do in this system. So to start that, in the beginning, all PCs were exactly the same. Operating systems ran on hardware because there was only one hardware target. PCs were essentially constant. Over time, the platform started to differentiate. There's added features, extra should be described, maybe a little bit more RAM, something like that. And over more time, more differences. Everything here is still literal, but it's starting to look a lot different. So the ACPI creators, who were HP, Intel, Microsoft, Unix, Toshiba, in 1996 defined a way to describe a PC platform to bake that description in BIOS so that they could couple OS with hardware. They wanted operating systems to run on hardware they had never seen. That sounds exactly what we want, which is, I think there's a good fit there. If you fast forward to now, there's an expectation that OSs work with operating systems on servers, desktops, laptops, using ACPI. I don't see a reason why we can't do that for switches. So the good things about ACPI is it's been around for 20 years, so you can argue that it's proof that it can be made to work one way or another. Nothing's replaced it so far. And maybe partially because of the problems in the early days on Linux, the tooling on Linux is actually much better. Logging facilities in Linux kernel are pretty nice. All the debugging tools, compilers, they're all open source. It's ACPI CA, ACPI component architecture project that uses all those compilers and debugging tools. It's all GPL. Everyone has access to it. On the other hand, it's complex, as in there's a lot of rope. For example, the spec is, the ACPI 5.1 spec is 980 feet. There's probably a lot you can ignore in there, but learning curve can be kind of high. Just knowing what you can and can't ignore kind of takes a little while to get your head around. You've got a 1,000-page spec to get through. But anyway. So, to give you an example of complexity, so ACPI didn't stop with just associating some static data with every device in the system. It's not like key value pairs. Like COM1 is at IO port 3 of 8, IRQ4. That simple system fact that you can just code as like a table. They didn't stop at that. You can actually write code into your ACPI that is interpreted by the OS's kernel and implements some of your driver control functions. So interpreted bytecode running in your kernel. What could possibly go wrong? But on the other hand, that's powerful in itself. There's all kinds of interesting hardware interactions kind of paper over. Some would call them bugs. Others would call them interface abstractions that you can handle with the right bit of data. And people definitely use it. There's definitely. So I don't want to discount it as just kind of ridiculous, but it is complicated, but maybe sometimes fun. So on the right-hand side of the slide, that's a bit of kernel documentation from the Linux kernel. I always like it when people try to do these crazy block diagrams with ASCII art. That was a good effort. But there's like tons of tables and pointers pointing in between them, like how you discover the tables, various formats of them. None of that's particularly human readable, but at the same time, help with things like that. So maybe it's a bit over-engineered, ACPI, but now we have to ask, can it solve our problem? Can it describe a switch? Well, we know it's mature. It solved a lot of the problems in early PC days when people were buying all their hardware at the computer shopper. And then it moved on to laptops and servers and desktops. But how are switches different than those things? Like what extra do we have to describe using ACPI to make a platform description of a switch? Well, fundamentally not much, but switches definitely look a little bit more like embedded systems than a standard PC. That to me means lots of GPIO, lots of I2C devices. We talked about that CPU switch case. Those are kind of the key. We need to make sure we can describe ACPI. So can ACPI 5.1 do that? The answer is, well, yes. In 2011, ACPI 5 added I2C resource description. That's a way to tell the OS you've got an I2C chip out on the bus at this address. This is the driver you should look for it, and this is what it's connected to. So there's definitely a way to encode that. GPIO resource description. This GPIO line goes out to the status element on the front. And then ACPI 5.1 added this thing called DSD, device-specific data. And that's kind of cool because what that does is it grafts a bunch of the functionality device tree on top of ACPI. Now ACPI has this sort of generic way to add key value pairs with all the devices in the system. I think those are going to be, I know those are critical for describing the CPLD and the switch ACPI. it's just a way to add those simple platform facts without too much work. Okay, so the spec supports it. What about the kernel? What about the Linux kernel? Well, luckily for us, folks at Linaro who are working on ACPI for ARM-based servers, which also look a little bit more like embedded systems, have been kind of gearing up to support ACPI on ARM for a while now. And if you look, May 2014, I can see research description of that with the kernel, GPIO 2013, BSD more recently, October last year. And it all works. Code work. So, the conclusion here is that after some research, and I think with a little work, I was convinced that ACPI could definitely describe all those extra switch functions, both spec support and actual implementation of Linux kernel. So let's check boxes on this ACPI. Baked into the BIOS, which means vendors can write it and ship it with their hardware. Can it describe a switch? Yes, with the recent second editions, and Linux supported, yes, with recent editions. So ACPI is looking good for modern sense, not the ACPI broken laptop. So that said, what is APD? Well, APD is a project, first and foremost, to kind of fill in the gap between the ACPI specs that can describe servers and laptops on one side, describes a switch. And to that end, it's an interface description, which is a document describing essentially device property binding for the switch ASIC. A schema, I guess, for describing how switch ASIC is connected to the front panel, all its buses, LED, port mappings. A way to describe the switch CPLD, so you actually describe the register interface to a CPLD and what this register is responsible for, say BSD. It's also some code. It's a set of generic drivers that run in Linux, and are generic and platform agnostic. It's one driver that can control all of the USB ports that are described. And along the way, I also had to add this concept of a pluggable driver. There wasn't a great generic device model for SDK pages, so we added that as well. And then finally, there's a bunch of kernel class drivers. These are the kind of drivers that will solve the mapping problem. That's what it. It's a way to ensure E0 is the front end port. It's a way to make sure that the silkscreen fan5 matches command line centers, which matches the user documentation that the user's looking for. If fan goes bad, you kind of want to get it all lined up before you go to visit the switch. So in addition to that, it's a bunch of tests and tools, and getting started or how-to guides and all that is to help lower the barrier for hardware vendors to describe the platform with ACPI and then verify that they got it right. One of the biggest things about ACPI, I told you about that 1,000-page spec and all the complexity. There's tons of ways to do the whole spectrum of application possibilities once you consider that you can write code in these tables. So APD is one of the most important things is to provide a guide. I would call it a set of sort of best practices for specific to white box switches that encourages kind of a reasonable implementation platform description. And we definitely want to avoid any ACPI broke my switch. So another way to put that is ACPI is the highway, APD is the agreement that we're all going to drive on the right side of the road. We will face all the signs in the right direction and draw some lines to how we're going to drive. So now that we have APD kind of specified, what does the new porting process look like? So I've got a slide here, and anything in green is kind of standards-based, documentation, tools are freely available. It's an open standard. And I've drawn those boxes as kind of stacked because once something's open like that, it can be done in parallel by multiple people, multiple hardware vendors, multiple OS vendors. We're working on that at the same time. The kind of pre-APD process is on top. The only green thing is Oni, and I guarantee you there's more than one person probably porting Oni as seats, so everyone can here, so it's not us. So what APD does is kind of move some of that work towards the OS, a significant portion of that work, over to the left hand of the side of that line so that it can become green or couldn't stack done in parallel. So Now I'm going to talk about testing. So this test box is kind of more from test certified. And with APD, there's a bunch of different ways testing can work. It's also kind of key today. But one strategy that I like is that testing is kind of done currently by hardware vendors using these APD tools to test suites and their own internal tools. And then also done by OS vendors with their internal tools plus the tools. It kind of gives everyone an interface to test against, which I think is a pretty good property. Along those lines, having an industry standard image to verify some of these things, maybe an OE diagnostic image, probably also a good tool that we can develop and give out as a part of the certification platform for APD. We also use the dotted lines around the ship box because, done right, the end of the process won't always be shipped in a box. And if it does, then having to do the shipping, not shipping the box, shipping it with OS release. Even if it does, hopefully those releases are kind of minor in regards to stopping porting. So, the end of the porting process doesn't always result in shipping. And, that means that, your OS release can focus more on it. So maybe I could even create a platform description for that first router that I coded to back in college. And I didn't realize it until I put these slides together, but that might be the theme. I've been trying to avoid doing homework for 13 years or so. So who wants to see some code? Raise your hand if you don't want to see code. A couple. So what I did is I took a description for alt switch, and I put device tree next to ACPI or ASL, these sources. The idea here was, if you know device tree, you kind of do a mental translation, get a feel for what it looks. This is using DSD. And there's no doubt the ASL is way less compact, but they're kind of performing the same function. And or good reason to build going around this, for sure. Yeah. But these two pieces of code.
Yeah.
I was going to do the demo. Okay.
Yeah, 20 minutes.
Yeah, okay. All right, let's start. So what I have here is a fully described Acton switch. That's the sound of a fully described Acton switch. So what I want to do is, this fully described switch has all the tables describing all the different switch functions, with one exception. I've commented out the fans. So I'm going to boot the OS, show you that it can't see the fans. I'm going to modify the APD description describing the fans, and then recompile the AML code, inject it into the system, reboot, and you should see the fans show back up. Just to prove that it's all wired up right, I'll go and pull fan 5, see that fan 5 starts to sure. So here's our, oh yeah. Here's our fan description. There are 5 such fans. The word wrap isn't great, it's a tiny console. But I'm going to take this hit 0 and turn it 1. Sort of do a git diff here. Show you that all I did was change it 0 to 1. 8. There you go. all. This update DSTT is a little building function for injecting a new platform description. It doesn't inject into the BIOS because it's demo, but it would be. So, I'm not going to read that. By the way, remember the slide where I said there's no air conditioning? So there's actually a picture of an air conditioner in that slide. So why would I show you a picture of an air conditioner if there's no air conditioning? Actually, that air conditioner was for the servers, wasn't for employees. So that works. I have to work on that later. Certainly, what I expected is you type sensors and you see 10s 1 through 5. But maybe I can use the rest of my 20 minutes to work on some code. We'll be at the booth. Let me finish up here. So, at closing, I guess what I wanted to say is, I kind of phrased this talk as a little bit of history, nostalgic stuff about this, maybe a little bit of a pitch about how I think it should be done, but that's not exactly true. I mean, we've got 2 fully described Acton switches here. We've got a bunch of kernel changes all queued up to go into the mainline Linux kernel. And Andy Quinn over there has been working with all the partners that you see up here to get some of their basically pilot program implementation. There'll be a press release tomorrow where we'll do their support of all these vendors. There'll be an APD GitHub repo that contains interface specifications I'm talking about. Anything that doesn't go in the mainline Linux kernel will show up there that you validate. And basically it. So, and then the other thing I want to say is kind of, obviously this is kind of a technically motivating thing to work on as an engineer, and that's kind of how I phrase the talk, but real motivation isn't exactly technical. It's about changing the industry. What we really want to do is bring that server compute out-of-box experience, that expectation that you can buy your hardware and software separately and they'll work together in the networking industry. And we're here presenting at OCP because OCP is all about open data center design, and I think APD is a great way to ensure that. So as a call to action, if you like what you're seeing here, tell your OS vendor you want it, and tell your hardware vendor you want it. And it's just not as useful. Rather than thanks, and I'll take questions, and I'll go.
Questions?
It seems to me we solve this problem upside down. So this all the hardware specific problem is a hardware problem, and then you solve by a software company by the describe to you, and then you write the trial part of it. Shouldn't that all push down to the ODM company? They're doing their own hardware to give you a standard interface. Is that?
By that, do you mean a standard software interface?
Yes.
So, I mean, you definitely want your customers to have choice in operating systems. And are you telling me that the hardware vendors are going to port or create drivers for every operating system customer might want? And that's kind of the reason you would want to do it. So you would have a platform agnostic, OS agnostic description of the hardware that can be used by any operating system customer might want. It really is just taking that process that's already happening, writing a PDF description of the hardware, and doing it in a machine readable way that really increases efficiency all around. Sure.
Any other questions?
No.
Much like what I said to the audio presentation, first quick comment, this is awesome, having seen your site. Well, the question is, when can I get access to the code? When can I start taking over Linux and taking advantage of some stuff you guys are doing?
Yeah, so I actually had an assignment to send all of my kernel patches right in the talk, but I already know how I am to publish, so I'm not done with the machine for that. But the honest answer is like this week.
I'm pretty happy to take alpha stuff.
Oh yeah, absolutely. And it'll become available on the Linux kernel now. Also the APG repo. That's a look there. So, totally committed to taking part of it.
What are your plans for non-x86 based platform?
That's a good question. Well, if the answer is ARM4, that will work given ACPI and platforms. At the beginning, I kind of called for a platform description protocol, and it worked out that ACPI was the right choice. Right. Other platforms will have other description protocols. Sort of forming BTS. Sure.
In one of your diagrams, you show the drivers as being kernel drivers. How much will kernel code is necessary? Because in looking at a lot of the switch hardware, a lot of it is I2C, access, etc., which really means that the real driver you have to have is really just the I2C driver, and everything else can be user space code.
Yeah.
So it seems like ACPI was a leap towards providing data for kernel level driver when this is all user space code. So is it that level of complexity necessary as opposed to like a YAML or JSON description?
Can you explain to me how this fits user space code, the kernel driver?
No, I'm not saying it's a kernel driver. I'm saying you can access kernel drivers that drive I2C from Python. Right? So,
well, I guess you definitely need description to get to that point where the OS runs on every single part. So the question is, where does that information come in? You're right, the I2C driver, the whole thing, we're definitely not rewriting that. I want to take advantage of it. What this code does is it's a way to take that description out of the ACPI table, instantiate the right driver in the right place, and kind of make it available to the output. So in the context of I2C devices, yes, not a lot of driving. More like if you know your Linux kernel code, there's this platform data structure that gets passed into a driver when it gets. This is a way to get all of that platform data out of the ACPI tables rather than having code it inside of a custom platform.
yeah, I mean, I've seen device tables that device trees that have a little bit or a lot. If you get the minimum amount, you get the same kernel boot everywhere.
Right.
And a lot of the remaining stuff, in terms of I2C, etc., it doesn't have to be kernel specific. It can be just data in user level code.
Right. That's true. I guess maybe to give you an example of one of the drivers that is a little more sophisticated, CLB driver. We're not just describing where it is on the bus, very simply load this driver. We're actually describing all of the registers. So there's basically some kernel code that is able to present all of those registers as sort of emulated GPIO or PWM cells or registers where you can feed back and
Yeah, my thought is if the more code you can get up into the out of the kernel, the less hardware specific code you would.
I kind of like the idea of getting more code into the kernel. I don't mean code that shouldn't be there. I just mean that HWMod, for example, type sensors. There's a bunch of drivers in the base kernel that pop up and say, I'm able to detect that there's temperature sensors out of the bus, and that's kind of the standard interface for how you guys work. So pushing things down to where components inside the kernel and components inside user space can interchangeably have a good position.
What percentage of these drivers? What percent? I kind of already know the answer, but what percentage of these drivers for temperature sensors advanced detectors we actually have the right versus or we just kind of describe them as drivers?
They're all already like every single one. And if we needed one more, we would write the kernel driver for it. So all this information, all these I2C device drivers are definitely coded one. Connected one. Give them a name. Give them a name. This is temperature sensor, that's front of the switch. Or next to the switch AC. Something you don't really have.
I just had one quick question, which was I was a little surprised when you showed the Linux kernel adding some of these 5.0 and 5.1 just last year.
Yeah.
It has been in there before, it's just different versions, or whether you're really starting with the kernel. That seemed kind of new to me.
Well, ACPI 5 is 2011, right? 5.1 is just barely July 20.
So the dates that you showed there, it's the first time Linux kernel is supported.
The left column was the ACPI spec officially. The right column was the first change that I could find. So, it was 2011, most of the work, 2013, really like a year. And, not to say that Linux hasn't supported a lot of the ACPI spec all along, it definitely has. But these specific things, the only thing I was custom. Because I think they're key to describing which one.
I have a question.
Sure.
Using the API, so you can kind of make the software standard. We have to base the standard hardware. I want to do something like special. So if I buy this company that add something like a new device.
Yeah.
So how the support this kind of things?
The best thing to do there is give me an example.
So you have to. We provide you the specifications, then you write the driver.
That's certainly one way it could work. You could also write the driver and get it. And that's kind of the theme here. We want to expose all this hardware using standard Linux interfaces so that software sees a standard interface using the hardware. Anything that's special that goes inside of that, definitely do. By working with kernel containers with OS, just like you do now.
Is there the way we learn your language so we can kind of support a new thing my own?
Yeah, I mean, all of this code is open source, right? Like, you can download the Linux kernel, make any additions you want. You can update the device property bindings for your special function. Get it as a patch to the kernel, and it'll flow into operating systems from there. That's kind of the natural order of things.
Thank you.
Any other questions? All right, cool. Thank you. So we have about 5 minutes before we start the next talk. Dustin was already busted by the Union Police, it seems, for moving the podium in here. You don't see this. Right, this isn't happening. There is no podium. So we have maybe about 5 minutes or so. So if you want to get some coffee, hit the head, whatever, we'll reconvene at 1600.
1600. Jesus, what are you European?
But I tell time in 24 hours.
I do too, but
I mean, honestly, I tell time on that.
I prefer GA. I should have done one of the ACP board of directors.
Was it joking or real? You didn't guys care about it?
Yes, did you see the guy come out and looked at us and gave us a lie? It's because we couldn't add any additional shit because OCP didn't want to pay for that because it's union labor. We're in fucking California, man. This is Texas is not a problem.
Now it's the they're trying to get out of PSD, which is
We didn't pay for parties.
the other stuff. They don't have to use PSD as much as these.
There's
No, but the issue is but what people really want, they want like $500 speaking. No, it is. I know. We need to work around the because you had got the free ESM. ESM right with a quiz saying well, which doesn't make the insurance
money's available. It's gonna be like an employee handbook.
So you know about ESM things like everything want to be able to put the switches in our carry on.
Yes, exactly.
And we can do some of the smaller quantum switches. No, the AML is not designed for that. So I ended up taking I was on the AML pretty long when part of the network was small. So and I'm able to, as you know,
What's he doing?
well, we're still fighting those problems.
So what is he on?
PGA. And I had these conversations like once a month about this stupid idiot did included this arbitrary string of this one. Now we're coming. Well, that's what's going in the 6.0 spec. The 6.0 spec is standard is. All it does was took the same exact operators there and lets you use it. This guy who invented it was a listens guy, and so he loved parentheses. And so Cameron Era that was yeah, it was AI. I was like, let's go. Go.
That's the way I roll, man. Yeah.
Yeah, so. Well, a huge amount of times we say device drivers, how do your device drivers say, how do I map certain things? Things like this. Well, supposed to because they've got a bunch of stuff there too. Yeah, exactly. I hope you do because they're.
No, I understand. Yeah, I think everyone existed.
No, you don't. You switch bus. You want to switch bus speeds between. But this I2C is going 400 megabits. Is going 1 megabit. That's the hard. That's the hardware per device. You kind of go out and talk to it. No, it's just some devices don't respond in 1 megabit and respond. You gotta go tell the bus master that device slow down here. I hope we stand right there. They're very expensive.
That's it. So,
already that buffers. These both share the same exact address, but the switch is over there. Yeah, exactly. Post-traumatic stress disorder. That sounds like the worst name for an ACPI table ever. Yeah, exactly. Well,
that battle is
good.
I wasn't here for that. Open API with your name. That's like a software. But it looks at open API. One, the first one, and they made the drug. Yeah, really, that's the thing. Look at here.
So it's
Great guys.
They specify the game specifications. They told everyone here, here's how you program. So their drivers are the best compared to so when you have things like that, you automatically almost
it's less than TNT, and after very good. Anyway.
Yeah, so they may all. So it makes it harder, I think, to have.
It is, well, exactly, that's happening. That's happening.
We'll get there when we get there. Okay.
Well, you know,
To some extent, we don't know.
so I was see, I'm officially old. You can date me with a magazine. Let's go to our trust on the exact same issues. Yes, it is already built. The SCI, if you go to this, not the sequel, it's all exactly the shove all their junk into the create. No one does that anymore. Yes, I remember.
All right, if everyone can take your seats, we're actually past time by 3 minutes. So we just be up 3 minutes, Bob.
Step down.
Cool. All right. So hopefully everyone will be trickling in. You in remote participation land, we realize there is a 45-second delay between now and in the future. So we will start now, and you'll see catch up in 45 seconds. So we'll turn it over to Bob. What the hell are those fonts?
Oh, you're going to not let me go on that, are you? My laptop does not like the fonts in the OCP standard slide deck, so I'm going to have to adapt. All right. Just going to set up here. All right. So for those of you still here, for those of you who might be trickling back, hopefully I think you can hear me well. It sounds like the mic's working. I'm Bob Noseworthy. I'm with the University of New Hampshire's Interoperability Laboratory, and I'll be talking with you a little bit about the work we've recently been doing with the networking project on the effort of component level validation, be it optics modules or other pluggable modules into the open switch hardware, as well as compatibility with various nodes. A little bit about myself. I've been with the lab going on 20 years now, starting with IEEE 802.3 and more recently in 802.1. So I've been heavily involved with the various Ethernet standards, including some 10 plus years ago, starting our 10 gig Ethernet test effort with that within the lab. So we'll go a little bit over what my laboratory is about and why we're here, what we're engaged with, a little bit about the philosophy as far as what we're trying to achieve with open networking, and testing tools and validation and integration that you've heard a recurring theme about throughout the day. We'll go through the Plugfest itself, recently held back at UNH, some of the results and outcomes of that, as well as steps forward. So one slide on what the university's interoperability lab is about. We've been in existence for over 26 years, starting with Ethernet testing and advancing on through the ages. Today, testing 100 gigabit Ethernet as well as IPv6, various storage technologies, high performance computing, you name it. We are a nonprofit academic organization. We are 100% industry funded, about 160 strong at the moment, many of which are students, undergraduate and graduates, in a relatively large 32,000 square foot lab. And we have been testing from 10 base T all the way up through 100 gig. We generally have silicon validation capabilities as far as bit level generation and observation, so we can work with all the major silicon vendors, make sure their components are working properly, do electrical and optical validation, do all the low-level analysis to ensure that components are compliant to the various 802.3 and other relevant standards. So this is idealistic, but I think largely congruent goal as far as what we're trying to achieve through the open networking effort. Certainly we want to have an environment where our end users, the consumers of these certified components and hardware platform modules, have a list of approved switches, approved DOSes, approved modules that they can, with confidence, plug into an open compute hardware switch platform and actually have an expectation with high confidence that the modules will work. So we've been working with the networking project for several months, if not years, depending on your perspective, and we have this pilot program underway. Certainly hope to have a certification validation effort within this year. This is a fairly unique organization in the sense of it is bringing together many different components. The end users, it's bringing together the switch vendors, it's bringing together the NOS vendors, the module vendors. We work with a large number of alliances at the lab, be it groups like the Ethernet Alliance or otherwise. They tend to have a slice of these pies, but to have the full spectrum of input as far as what is desired and what needs to be validated, I think it's exceedingly beneficial. It's very nice to be able to hear from end users directly that this is what we're trying to achieve, this is what we want to use in our data center, and this is what we are trying to do in a large-scale deployment. So I was going to call out Bob, I think he's still on break, shame on him. But we've been working with Fidelity for several years, and we've been working with other end users for several years. So this is just one quote Bob recently gave us for the plug test that we recently held. It's inarguable that module interoperability is valuable for the end user. What some in the room might not appreciate is it's actually not common. It's exceedingly common to have a whitelist with your OEM switch provider where only these modules will actually be allowed to work. And if it's not one of the approved modules, it won't be enabled. So to have an open networking environment where you can have open switch OCP hardware tolerate and accept and be shown to work with any pluggable module, any DAC, any sort of active optical cable, is actually quite empowering, I think, for the end user. There's a recurring theme here throughout the day, perhaps you've noticed, a wonderful funnel diagram. In this case, my simple summary of Carlos's and others' previous points is there are components being defined that are clearly in the open source community, clearly OCP specific and centric, and certainly need to have a certification and validation program for those discrete components. But there is the bigger piece of the pie here that we need to look at. So to recap, with a little bit of speed, just since it has been mentioned several times today, the component validation pieces we've heard ONI several times. We've heard APD, we've heard of SAI, and I'm sure what will be an interesting validation effort of that interface as that continues to emerge. And all of this certainly has an OCP context to it in our view. But these are just the component level pieces of an open networking environment. We need to include those components that aren't necessarily OCP contributions, that aren't necessarily fully open, yet integral to the functionality of your network, especially in a non-greenfield situation where you're looking for compatibility with legacy hardware. So here in this case, of course, we're looking at NOS vendor solutions. We're looking at modules, be they optics modules or cable assemblies, or any other sort of other technology, NPUs or otherwise. So the integration of those components is where we focused so far with the initial plugfests. And we are talking pluggable module into the open compute switch environment with various NOSes, right? It's straightforward validation, but not as easily defined as simply does this one singular open source component work. And then we get to the how do you interoperate with legacy equipment, the non-greenfield environments. You want to deploy OCP switches, and part of your networks may be at the leaves, but not in the spine, wherever your case might be. And here, traditional interoperability, such as we've been performing for 26 years, makes a very simple step forward as far as now do this with OCP hardware and validate all the various routing protocols and interoperability of the underlying hardware with the more traditional closed switch environments. So, at least from my perspective, focusing just on this problem of pluggable modules, we need to be addressing the host-side electrical validation of the network switch. We need to be evaluating the NOS compatibility, and we need to be evaluating the module to ensure that these modules will work, at least from a compliance perspective as well as the interoperability perspective. In my world, you can't have one without the other. Interoperability will demonstrate that these exact instances happen to work under these scenarios. Compliance testing helps predict future interoperability. Doing only one only gives you a piece of confidence towards your end game. Having both helps establish a higher level of confidence for the end users. Compliance testing is only so complete, it's only so accurate, and perhaps there's only so much time or money that is suitable to be expended on the effort. Interoperability testing at least demonstrates that it actually worked. Finding a balance between the two is what we're after here. We've talked today about various other efforts, the Only APD and whatnot. So again, just focusing on network module certification. And this is what we focused on at Plugfest, which was back in February, up in Durham, New Hampshire, where there was, I think, only a little bit of fresh snowfall, which was surprising, actually. We went 3 days with only 1 day of snow, so yes, that was good for us. For this first event, we were focused mostly on module management, simple EEPROM reading and such, host electrical validation, and basic link functionality. But we certainly expect coverage of required tests to be growing as we move forward. See one of our students working on some of the electrical tests in the picture here, some of the test setups with loading up all the ports and switch under test. Those pictures there. Some of the participants, I think we've already covered this in earlier slides today, but just to recap, we did have end users both feed into what should be tested as well as present, giving some input and observing some of the operation. From Fidelity, we had the active switch, thanks to Jeff and his team. Mounts vendors from Big Switch and Cumulus, and of course module vendors and all Argo Technologies, Finisar, to help really bring this together for a pilot of how to validate open network switches. As expected, a lot of things went well. A few highlights from the event. We did use the Gerbers provided from Acton to inspect the design of the board, to identify 6 ports that we wanted to focus on of the 48. Again, this balance between how much compliance testing do you do versus the time and energy you want to devote towards it. So some intelligent selection of ports. Sure enough, when we inspected the ports, we identified, okay, those should be the 2 worst because they have the longest trace. And of the 6, they certainly were the worst. I'm not saying they weren't compliant, but they were the worst versus the other 4. And for our purposes here, we're just talking transmitter I and jitter. Obviously, return loss and some other things can be looked at in future events. A couple other obvious things, perhaps, at least if you've been doing this as long as I have. If it works after 20 minutes, it's going to work overnight, right? We're not getting down to the 10 to the minus 21 bit error or anything crazy like that. But at these 10 gig speeds, it doesn't take very long to establish, is the link suffering from some serious problem, or does it look like it's certainly well beyond 10 to the minus 12 required by the spec, and probably out past 10 to the minus 15, 10 to the minus 18 as far as reality. So again, time versus money, right? We don't need to set up a certification program that requires overnight testing if we can get the same results in 20 minutes. Some of the problems we encountered. It wasn't just a clean, smooth sail run through everything that what little we might have done in those few days, snow aside. So we had a good mix of parties, lots of different products from the different parties, it wasn't just one from each. And we actually encountered a scenario that, sure enough, only reproduced with a specific switch, one specific NOS, and one specific cable. And didn't seem to be just a one-off fluke of a bad performance for such. So that's interesting, right? You need to do this pair testing. You can't just do compliance testing on just the switch platform or some sort of software-only test on the NOS. You want to look at the interaction of the NOS with the hardware, how it configures the SerDes. You want to look at what the module is reporting itself as. You want to look at electrical behaviors of the switch. Try to look at this as well as in concert together for interoperability assessment. Not too surprisingly, we ran into a couple management issues with modules, slightly incorrect information on what they were reporting, or at least what the NOS was indicating they were reporting, I think. And just a final point here on the testability aspects of these platforms. The various standards require various test modes, and if we were to require, as part of OCP certification, certain validations that require those test modes, then perhaps maybe it's an ONI special test firmware that can be loaded on the switch to validate the silicon, or maybe it's functionality that needs to be built into every NOS. Those are all things to be debated as far as how to get various test modes required. So that's the quick takeaway from the brief event we had. Certainly as we move forward, we need to consider programs to validate the network switch, and those programs will be a slightly different color than the programs for the modules or for the NOS. It's not going to be one test plan for all three, but there will be a great deal of similarity, I would suspect. I think to restate this end user goal, we would want to live in a world where you can take any OCP verified module and plug it into any OCP verified switch and actually have an expectation that this will work with whatever NOS is running on the switch. It's simple to say, but again, it's such a different model from what currently exists in the networking world. So far we've been focusing on the network switch. These other module-specific and NOS-specific test plans just have to evolve, which is sort of the phasing here, where we're not at an official certification program yet. We've been working on the switch validation, verifying the electricals there, but working towards verifying host-side electrical behaviors of the module. We're talking the SFP plus interface, the QSFP interface, making sure that those pluggable modules conform, whether it's to SFF specifications or otherwise. And of course, some level of NOS testing. It might not make sense to do electrical testing on the NOS, but if the NOS is configuring the SerDes incorrectly, well, that will cause problems. So maybe there's at least a minimal amount of verification that still needs to be performed as we switch between one NOS or another. Coming out of the PlugFest, the participants have the various results, some of which are presented here. A more detailed report will be available to the participants and eventually on the wiki for the larger community's awareness. We certainly intend to continue to work with the networking project to define and refine the test plan for the various areas mentioned, not just switch-focused, module and NOS-focused. Tentatively, in late spring, there will be another event at our facility, if not late spring, early summer. Keep the cadence up and the pace up here so that we can move forward and continue to expand and define these test plans. And hopefully get to that last goal here in 2015 of getting a list of verified switches, modules, and NOSes out there for the end users to help make more informed decisions in their purchasing of OpenCompute hardware. There are many events here. There's a large 25, 40, and 100 gig event at our facility June 22nd. We'll talk to me afterwards about that. But that's just pieces of what's happening in the industry. OCP is bringing together a larger context, so continuing to work with the networking project here to define what the OCP community needs, what the end users are demanding, helping to organize that set of testing between component validation, integration, and interoperability. I think it's critical, and having the input from those of you here is exceedingly valuable. So for those who've helped us get to this point, and those of you who have participated in the recent activities, my thanks. And for those of you who want to get involved, the door is open. There's nothing exclusive here. We want as much input and involvement as possible from the parties involved in this effort. That's all I have for the moment. If there's questions or additional commentary.
Yeah, so just kind of add on to this. It's hopefully by now your head's not hurting too much by all this pounding on testing. I don't want to take on the whole developers. Like, where testing, interoperability, that's the key for us to actually grow and to make open networking a reality. Quick show of hands. Who are the end users and operators? What's more important for you? Or I guess what is your priority list to adopt open networking hardware, software? Here you go.
Sorry. That we can pick and choose our components, and they'll interoperate flawlessly, so we don't have to get calls by VPs at 5 in the morning wondering why stuff isn't working.
Mm-hmm. And why you didn't just go with some other traditional vendor or whatnot, if this is the case? All right, anyone else have a different take on that? Or is that pretty much summed up everyone? I think it pretty much summed up everyone. So, with that, it's, this right here is just crucial. So, I know this is probably not a democratic way of doing things and whatnot like this. So, if you would like to see or participate in further events at UNH, let me get a show of hands. If you're on the IRC, hit +1 or something like that. We'll see you in 45 seconds. So no one wants to see this happening? All right, come on, raise it a little bit higher. Higher. All right, while we're doing that, how many would like to contribute to make sure that it stays happening? Okay. All right, it wasn't a whole one-to-one, but I got a list of the serious people. Anyways, that's cool. Hopefully, we'll make serious takers out of everyone over the next coming months. We'll see the benefits of what this type of testing really drives in our industry. The next thing I probably want to mention, and not to kind of belay the point, is remember that last bullet point where you said a list of different switches and modules and NOSes? What if we put together a consumer's report style service for everyone out there? Let the users choose and see what platforms they want to see, right? They select their switches that they were interested in. Next, they can see what NOSes can run in those switches. Next, they can see what optics can run on those combination of suite. And finally, they can see what it interoperates with. All while seeing and having access to the full test reports. So they can verify and qualify this actually does work. It's a 5 out of 5 stars, as I guess, what is it, the Highway Association, like, yes, crash test rating 5, the highest one out there, right? Imagine that with open networking. Who wouldn't adopt that, right? Because what we just did was we just made it a democratic, available access to all information about these devices. I mean, they can see MSRPs on websites. But what they can't see right now is the testing information to make informed decisions on, should I go with this optic or this optic? Well, this one is this price, but this one is this price plus delta. Well, if they can see from the test reports that this delta really is worth it, guess where they're going to buy? Right? It's the same decision tree that we make whenever we buy cars. I hope. Right? Probably not. Right? This is California. Everyone just walks. Right? This only matters in like places that we have like trucks everywhere. Come on. Yeah.
I just want to give some color because my name's on 4 different talks and I haven't stepped up yet. I'm Matt from Cumulus, and I just want to give a little bit of translation to what Carlos is talking about. When you look at ONI, for example, that Cumulus donated, ONI, the software was contributed before we defined kind of the end results. Right? As you saw from Dustin's presentation, frankly, it was self-serving for Cumulus, right? We didn't enjoy bringing out the JTAG every time we wanted to port our OS to a platform. Felt that was a benefit to the industry. But we didn't define as OCP the test criteria of what a ONI OCP compatible switch is until a few weeks ago when we actually enforced that with testing. So what Carlos pointed out earlier today of this automated test suite, that references a document that we wrote, I guess probably about 6 or 8 months ago, of the testing criteria. So if you look at that, we did ONI backwards, right? We put source code out, then we defined what that standard was, and now 2.5 years later, we have a testing suite. So what we're trying to do is fix that up a little bit for the optics, for the NOSes, and be a little more holistic about it. So it's really important that the end users that are here today, whether you're from a financial organization or a cloud company or wherever you're from, to give us feedback on what we should be testing for. So for example, when we did this first test, we focused on 40 and 10 gig platforms within the data center. So we didn't use any 80-kilometer optics. We didn't use a lot of exotic breakout cables. And with Jeff's contribution from Acton, right, this is a 100-gig switch. You saw all the different modes that are available in it. We need to know what optics you want us to test and what configuration. So if you could give us feedback, that would be really useful to scope the next plug fest. And also your feedback on what's burned you and what's been successful in the past. Because on the testing front, we can do a lot of testing on the optical side, but frankly, someone like a Finisar or Vago has already done that. The problem is likely going to be on the electrical side and the signaling side. So again, give us your use cases where you've been burned in the past so we can incorporate that into the test document. And then the other thing to highlight is that this past event, that was self-funded. So all of the vendors that participated, the hardware vendors, the NOS vendors, and the transceiver vendors, they all contributed money to do that event at the IOL lab. And so if we want to continue that, we need to figure out a fundraising mechanism for that. So I would encourage you to talk to folks at the OCP executive level like Amber and whatnot and say, hey, how can we get OCP to kind of sanction these plug fests going forward? How can we get this funded and have this cadence? Because again, we're NOS vendors or hardware vendors or optics vendors. We assume that if we were in a customer position, this would be valuable. But frankly, customers speaking up, whether it's with money or it's with standards documents, it's really going to drive this process. So hopefully that gives a little bit of a slight translation there of what you've been kind of dealing out with the testing mantra. So if you have any questions, talk to any folks here. We had a great time in New Hampshire for the week, and the weather did for us a little bit. So got -20, I think, one time.
It's good for him.
Yeah, it was a heat wave of 30 degrees Fahrenheit, yeah.
Thank you.
Cool. So up next, we have our last talk for today, and that is open optics.
Okay. Good afternoon, everybody.
Yeah, it's my turn. You want the lab or do you want it?
Okay. Yeah. So that's simply looking for the idea to put that in my box, that's it. Okay. Okay, I assume you can all hear me. Good afternoon, everybody, and it's a pleasure to be here. What I'd like to do today, at the end of the day, is to first of all ask you how many people know anything about silicon photonics? Wow, a lot more than I thought. Let's see how many of you are still awake by the end of this talk. So what I'd like to do is announce, first of all, the Open Optics MSA. I'm not going to go through a lot of details. There's a lot of information that we have actually announced today and put in public. I'm going to try and paint a little bit of the scenery for it, the background for it. I'm also going to try and do a little bit of an introduction or tutorial on silicon photonics using some of the technology that we have at Mellanox as an example. There is a lot more information on the web, and there's a lot more information available today that we released. So first of all, what is the background and the motivation for this MSA? It's really to enable a high bandwidth connectivity, so that the next generation data centers and high performance computers have the intelligence and the smartness that they need to be able to service our needs going forward. And a lot of this demand is coming from the fact that now we like to communicate with images and motion images if possible. They started like that in our history many, many thousands of years ago, and we seem to be keeping it up. We'd like to send pictures and movies if we can. Now I'm getting, instead of text messages from my wife or daughter, I'm getting a picture. And it annoys me because I have to actually click on it to find out what they're trying to tell me. And then I have to guess what is the message. But that seems to be the preferred way. And of course, it's good for our business because it requires a lot more bandwidth. And who doesn't like more bandwidth, right? So when we say smart, usually it means a lot more bandwidth, and it means a lot more connectivity. So a normal phone in the old days had a capacity of, let's say, 1. A smartphone is using typically 30 times more bandwidth, and of course a tablet uses over 1,000 times more bandwidth. This is coming from the fact that the text is usually only about 1 kilobytes of data. A picture is megabytes, and a movie, of course, is gigabytes. So a demand on bandwidth and storage and so on is increasing exponentially. We used to say a picture is worth 1,000 words. Actually, a movie is also worth 1,000 pictures. And in terms of bandwidth usage and the storage space, it actually goes in those proportions. Now, this means that we're having major growing pains in our data centers, in our racks, in our boards, in the chips we design. And in order to accommodate this, we need a lot more bandwidth, a lot more connectivity, and at a lot more lower cost and lower power. So what are the customers are asking us? The customers are telling us that our current solutions are way, way, way under capable, over costing too much money and under capable, and that they really want us to be. Do we have a laser pointer by any chance? No. Okay. So what they're really asking us to do is transfer a huge amount of load at much, much faster speeds for much lower costs, consuming a lot less power. That's actually quite a tall order. Thank you. That's good. Thank you. So in order to achieve this, we believe silicon photonics is well positioned to come up with very innovative solutions. Under the Open Optics MSA, we are creating the ecosystem that enables us to do this. But let me tell you a little bit about silicon photonics, a bit of a background. So basically, silicon photonics uses the existing CMOS capabilities and manufacturing infrastructure to come up with integrated optical solutions. Key materials are silicon and germanium, and we like to operate on the 1.55 micron wavelength. so that we use silicon where it's transparent, and for active devices such as motion detectors, we use germanium. This enables us to detect light, to modulate light, and maybe even to emit light one day in the long distance future using germanium and silicon germanium compounds. It utilizes we prefer the 1.55 micron wavelength for this work because it utilizes the advantage of germanium very effectively to do very efficient modulation and detection of light. And of course, silicon photonics brings many advantages. As I mentioned, one of them is the capability, the use of CMOS manufacturing infrastructure to have a very cost-effective and high-yielding products. Integration reduces assembly and packaging cost. Packaging and assembly is about 70–80% of the cost of any optical product. So to eliminate that is key. Integration in itself is only a means. Improves reliability and operation at higher temperatures. Operation at higher temperature is actually quite important because in order to enable more bandwidth, what we're having to do is transfer the transceiver and get it closer and closer to the ASIC. As we get it from the panel into the board and ultimately to the actual ASIC, the operating temperature has to go significantly higher. So for example, some of the technologies available in the open optics MSA, for example, through our partners Ranovis, is very important, being able to have lasers that operate at high temperature. Another key benefit of high temperature is that if your data centers operate at higher temperature, then the power consumption is low. So that's also very important. Of course, silicon photonics also offers improved reliability. Semiconductor-based devices in silicon are very reliable, but also the lasers that we utilize are telecom-based and therefore have much higher reliability. And that's a key, again, requirement for being able to put the transceiver on the board and next to the ASIC, because these are not going to be pluggable eventually. You want to be able to have the reliability so you don't have to open up the racks all the time. And also the silicon photonic-based devices are based on single-mode fiber and are very scalable in terms of not only bandwidth, but also reach. Now, there are different types of silicon photonic waveguides. We refer to them as silicon photonics, and a lot of people think there's just one version or brand of silicon photonics. It's similar to the story about the turtles. There are many different silicon photonic types of devices and geometries and dimensions. A lot of the people in the field are actually working with the small waveguides. These are waveguides that typically are only a fraction of a micron. We actually at Mellanox work with the larger waveguides, which are about 3 micron or 4 micron across and tall. The platform is based on a long heritage of real products. These are some of the products that Mellanox, before that Coutura, before that Bookup developed on this platform. So even though we may be alone in terms of companies that are developing products on this platform, I would say that there are more products developed in this platform than the rest of the players in silicon photonics added together. So there's a long heritage of products based on this platform. And other people also think that silicon photonics is a new thing and there are no products out there. That's not true either. There have been products in silicon photonics for the past 20 years. For example, one of these products, the VOA, what is it? Here, has actually been in production for almost 20 years and is constantly carrying traffic in the telecom system. We have
limit your speed to about 10 gigabits or so. What we did was basically rotated the device geometry. We rotated it by 90 degrees, put the junction on either side of the device, and that way the carrier transit time is limited only to this half a micron or so. And you have still a device that's about 3 micron tall. And it's really the height that's the problem when you want to manufacture these devices in a small foundry. It's not the width, because the width is just a mass design. It's the height that creates the problem. So we solved that problem. That very innovative design enabled, that key innovation enabled us to move from devices that could be limited at about a gig or so to devices that can potentially run at 100 gigabits per second. So the speed limit was completely removed. So this enabled us to have all the benefits that you need in a product like this. Very low loss waveguides that are independent of polarization, WDM, very high speed, and of course the capability to integrate 3.5 components. Very ready. And this means you have many different dimensions in silicon photonics to increase bandwidth. One is the speed, as I mentioned before. Here we can support speeds up to 100 gigabits per second if needed. Wavelength counts, we can go up to 80 or more. Of course, we can have more physical channels, more fiber, more waveguides, and of course the modulation, complex modulation schemes are available. If you add all this together, you can see that there are many orders of magnitude increasing bandwidth that we can support with an integrated solution based on silicon photonics. So today we announced Open Optics MSA. The key members are basically so far Siena, Oracle, Vertilus, EOC Quantum, Ranibus, and Mellanox. Mellanox and Ranibus are the founding members. The aim of the MSA is to create a highly innovative environment ecosystem to enable the next generation photonic solutions for data center and HPC. Unlike most other MSAs that are very, very specific and define everything to the last digit, in this MSA, we are trying to deliberately be as open as possible. That's why we call it Open Optics MSA, and allow room for flexibility and innovation. And we believe that the right solutions over time, with interactions with the customers, will develop. We're just trying to create a framework and enable innovation and the collaboration to come up with the right solution. And at the heart of this MSA is the C-band, the wavelength, which is based on the long heritage we have from telecom. The telecom guys solved these problems 20 years before, and there is no need to reinvent the wheel. They went through this whole motion of how do I do a lot of bandwidth, how do I transport it, how do I make it cost effective, how do I make it work. And there's a lot of good technology there that we want to reuse here. There's no need to reinvent the wheel. And what we want to do is actually base it on the C-band, because that is where we have the densest number of channels. The commercial environment exists, the infrastructure exists, the tools exist, everything is out there. Try and buy a tunable laser at 1.3 versus 1.5, 1.3 costs you about 10 times more, just because WDM infrastructure doesn't exist at 1.3. So if you want to do dense WDM, the 1.5 micron is the wavelength to be, and all the infrastructure exists. You also have all the technologies that we need for implementation of such solutions at 1.5. So that's very important. What we're proposing under the MSA is a grid at about 200 gigahertz, not the 100 gig. And IQT grid enables that. They actually have a very flexible grid environment. People operate at any grid. As long as you're on the IQT grid, it doesn't matter what the channel separation is. You can go down even into 25 gigahertz channels. So we're basing it on the IQT grid, and we're proposing a 200 gig grid, and I explain that later why. So this is the grid choices we have proposed. These are based on 200 gig grids. And what I have done here is just an example of what you may be able to utilize or propose for 100 gig aggregate bandwidth, 200, 400, 800, and 1.6 terabit per second, depending on the different channel spacing you may choose to do. And the whole idea behind the MSA is that you can change the channel separation to come up with the most optimum solution for that given product. At lower bandwidths, 100 gig, 200 gig, you don't necessarily need to go for very narrow channel separations. The lower channel separations typically reduce the cost. The reason why the cost is reduced is because it eases the thermal management. Also, the component registration and accuracy is not as strict, and that also helps a lot with the cost reduction. And however, smaller spacings offer the most spectral density and efficiency. And of course, fewer gain elements, which is another key driving factor for cost. So you can compromise between those two. So a key deployment for WDM is the registration of WDM devices. Most WDM most optical components have a performance that is wavelength dependent. Their performance also is temperature sensitive, and on top of that, they are very dependent on manufacturing tolerances, and the response can vary greatly with how you make them. That makes life very difficult. It's effectively like shooting through a number of keyholes. You have to make sure your wavelength is right. So, for example, here what I've done here is to draw the wavelength response of the different optical components. Starting with the gain element of a laser, it's very broad, typically 40, 50 nanometer. It moves with temperature at about 6 nanometer per degree C. The laser grating, quite often the device that sets the laser wavelength is a very narrow bandpass, but by definition, because you're trying to define a very narrow spectrum of light. It's less than a nanometer, and usually goes with the index of 3.5 or of silicon at about 0.1 nanometer per degree C. We use an FK modulator, other people use other modulators, but this device has a bandpass of about 30 nanometer and moves at about 0.75 nanometer per degree C. Mux demuxes in silicon go at about 0.1 nanometer per degree C, and their bandpass is really a function of channel spacing. It's usually 30 to 50% of channel separation, whether you use a Gaussian or a flat top structure. And the detector is very broadband, quite often in a few 100 nanometers or so. So you have to line up all these devices, and you have to cope with the temperature dependence and variations and manufacturing tolerances in order to make it WDM system to work. So, for example, this is the bandpass spectrum of a mux-demux structure. And what you have to do is look into the bandpass, typically the 1 dB bandpass, and define your budgets and say, okay, how much do I allow for the wavelength, accuracy of the laser, how much I allow for thermal drift, how much I allow for the wavelength registration, and then try and minimize this so that you can basically increase the spectrum efficiency of the overall solution. And as you do this, and you make trade-off choices that impact the cost of the product. For example, if you go with a 0.1 degree C temperature requirement, you're going to have a very expensive thermal design on your hand, but you can really go with very high densities. You can support in excess of a terabit per second. If you wanted the low-cost component for 100 gigabit or 200 gigabit, you probably want to go with wider channel separations and much more relaxed temperature stability solution. And that is the beauty of the Open Optics MSA, that enables you to make those choices and innovative solutions based on this platform. Specifically at Mellanox, we have a laser cavity design, which I will explain to you in a few moments, that basically tries to make the right trade-offs for our specific solution. This laser solution is able to define the wavelengths very accurately and cost-effectively. Given the technology is based on silicon, we also are able to make the wavelengths very well and have a very cost-effective solution. Now, if you are able to come up with the right solution with narrow channel separations and still decided to go with very fine wavelength spacings, it's okay, because if you really go with very high bandwidth, you can amortize that cost over many gigabits and many channels. So let me show you the difference between this MSA and, for example, the CWDM MSA that was announced a few months ago. In this arrangement, what we have is only a few channels far apart, 20 nanometer or so. In this case, each laser is 8 thermal, so the gain spectrum of the material can swing. As I explained before, it swings by about 0.5 nanometer per degree C. And this means over a 70, 80 degree C temperature range, this gain spectrum can move by 30, 40 nanometer. And the bandpass of the gain spectrum is typically only 40, 50 nanometer. So you're on the edge of a design that doesn't need thermal control. It is a thermal. And you will need one gain spectrum, one gain material per laser. So you cannot really use an array easily unless you temperature stabilize everything. And if you temperature stabilize everything, then you don't really need to go with such wide channel separations. You can go with much smaller channel separations, as we are proposing. So this solution is okay for a 4-channel, 20 nanometer wide separation, but it's at the limit of what it can do. So if you wanted a scalable solution to 200, 400, 800, you would have many challenges. It's not very scalable. Whereas the open optics, let's say, channel plan enables a highly scalable solution. We have the gain spectrum moving, but it's still within the range of 10, 20 nanometer. There is enough gain to enable the solution. So you could even not temperature stabilize all the elements. For example, the gain element doesn't need to be temperature stabilized with the solution. You can only temperature stabilize some of the components and still have a working solution. But you could temperature stabilize, you could deploy, for example, a couple of gain elements, and you can cover many, many wavelengths. You can go to 32, 64 wavelengths and have very high aggregate bandwidth. At the heart of this solution for Mellanox is the external cavity laser that I mentioned before. Here, what we basically do is put a grating that selects the laser wavelength in the silicon and not in the laser itself. And that enables a very cost-effective solution. Here we can therefore generate multiple wavelengths from a laser like this. The wavelengths are very accurately defined. You can see the performance of the laser is very good. And basically it matches the DFBs, which are very expensive in terms of performance, and it comes at a fraction of the cost. Here is for example, the reliability test on this device. You can see that we have the highly accelerated aging tests going out for quite a while now, this past 10,000 hours, which basically, those kind of acceleration means the device life is proven for well over 7-8 years already. The solution is highly scalable. You can integrate a 10, 12, 15, 20 channel device without a problem. Since you're only hybridizing one die, it means you don't have to flip chip many dies. You can get many channels from one placement. And it's the accuracy of the placement that's very important. So if you have to put many of these dies, it's a problem, because even if the yield is 95%, but when you accumulate those, that becomes a problem. You really want to get as many channels from one die as you can. So here are the kind of options that we have available today. There are the Fabry-Perot lasers, which are by far the most cost-effective solution, but they don't support WDM. You have DFBs, on-beam, and beam. You have tunable DVRs, and you have silicon photonics external cavity lasers that I mentioned to you before. There are other solutions here that I'm not covering, like there are external cavity lasers and silicon that are based on rings. For example, Nanovis is working on a similar structure that utilizes rings. We use the grating. But those devices also have many benefits that I won't cover here. And these devices are able to scale to very high bandwidths, aggregate bandwidths, and go in excess of 800 gigabit per second or even into the terabit regime without a problem, whereas most other solutions, the CWDM solution that I mentioned before, utilizes the DFBs that get saturated after a while. So this solution is able to scale to very high bandwidth because of that. So the laser is at the heart of a WDM system. So for example, with the proposed solution here, we can go up to, we can utilize these channel spacings. You can see that I'm shrinking down from 8 gigahertz channel spacing to 200 gigahertz over, as I increase the number of channels. And ultimately, I still need only 2 gain elements. Each gain element may give me 10, 20, 24, 30 channels. But because I have so many wavelengths, so many channels on each die, I still need to only hybridize 2 channels. And the thermal management complexity is still very moderate. 10 being the hardest and 1 being the easiest. By 10, I'm referring to, say, 0.1 degree, and by 1, I'm referring to 5 degrees. So it's still very easy. What I want to do in the last few slides is just give you some feel for some of the products we're developing. One of them is a CIP active optical cable. This device is able to transmit 100 gigabit per second over 2 meters of fiber. The target BER is 10 to the minus 15. You can see here that the BER is fully satisfactory up to 200 meters, even beyond to 300 meters. The eye opening is very good. The NUI margin is well over a third of the bit rate, even with the CDR off. So, but of course, when you put the CDR back on, it improves the performance of the device even more. This is the device without the CDR, with the bathtub, and this is with the CDR. You can see that we have a very wide eye opening here. method third of the bit period. The next device, the next product is the transceiver. Here the target reach is 2 kilometers. The idea is that when you design your HPC or data center, you don't have to worry about how far away do I put the cabinets, where is the storage, where is process capability, and so on. It can be complete, the architecture can be completely open. The device is actually capable of more than 2 kilometers, but we are targeting, we are expecting it only at 2 kilometers here. You can see that at 2 kilometers, the panoff is only 1 dB, and most of this is dispersion. But there is a lot more margin there. So even without the CDR, we still have well over 200 NUIF margin. And of course, the WDM is a key product for us and supported by and this is within the framework of the Open Optics MSA. This is a demonstration of that here. You can see the food, this is the target footprint is QSFP. We demonstrated at OFC last year, the year before. And you can see that we have the eye here, the 25 gig eye, or up to 2 kilometers of fiber. Still very nice. You can see that we're using the external cavity laser structure here. One single die element is able to enable 4 wavelengths, and the performance of the device was very good, and we're now commercializing this product. I'm done. Thank you.
Any questions? All right.
A couple of comments and perhaps two questions. First, I believe silicon photonics is really urgently needed, and the time to use the external optical module SSD, they're too expensive, cumbersome, and so on. That I agree. However, I'm a bit concerned that this presentation doesn't seem to be as an industry pitch. When we lack vendor like Advego, Wixter, or Intel, and so on, it needs to be a true multi-vendor type of solution. This seems to be extremely Mellanox specific. And when we talk still these old type of connectors like MTC and so on, so way too expensive. There's the industry need to get this act together, because otherwise all these white boxes use the old technology and establish networking vendor selling the new technology, and they will be able to be even cheap than the open source hardware if the industry will get that together. So I would like to know, what are you doing to welcome these other companies?
Anybody who likes to join the MSA is very welcome to do this, but the optics industry is still highly fragmented. Different people are coming to it from different angles. It's people have different technologies, different backgrounds, different capabilities. It's very hard to get the optics industry to unify around one to MSA. So you're right. We do need more people on the MSA. We are working to gain and get more people to join us. However, it's a very slow process. It takes time. It's not easy to do. People have spent 20, 30 years to develop a capability. The R&D dollars are very scarce in this industry, and it moves very slowly.
Maybe a follow-up. I just had a question about what do you hope? So the Open Optics MSA was started maybe a year ago, some time ago. You and Ron Reynolds. What do you hope for from OCP? In other words, bringing it to OCP. What do you hope from the community here? Like, do you hope for us to say, okay, yeah, that's interesting technology. Do you want us to give feedback? Do you want us to say rather this than lasers or MEM stuff? Like, we should go this. You know what? And how is it different from where you were with the MSA? What do you hope for?
We'd like to get an acceleration of the acceptance of the MSA and hopefully use the customers, the end users, to get more people join our MSA. As the previous question asked, we need more members. And we are working with people, but at the end of the day, the only thing that motivates people to do things is the customer asking them. So I think here is the end user customer, the end user environment. We'd like to talk to the end users and get them to see the value of the MSA so that they can create and stimulate the ecosystem. around the MSA, and so that more and more people will participate.
Maybe you help me understand what's the value of MSA versus OCP? In other words, you have the specification, you have this technology. Why? I'm trying to understand, like, how do you want to pursue the technology?
Look, any MSA usually requires a vehicle to go out there and get publicized. A lot of people use IEEE. In the case of 100 gig and 400 gig, IEEE seems to be incapable of adopting the solution, mainly because everybody is driving in a different direction. And so we could go to IEEE. We decided to go to OCP. We believe that the end user at the end of the day is a more appropriate environment for us to introduce our platform, introduce our MSA, rather than go to an environment like IEEE where there are a lot of people fighting over different possibilities. Sure, of course.
So I think it's a very good question, very fair question. As you may know, Omar, there's been a lot of RFIs industry over the last year asking for company perspectives on how they're going to address the 100 gig WDM market and how does that then scale to 400 gig. And so we have actively participated in those RFI responses. We have a very clear solution that we have in mind, which is single mode fiber. And Arlen over here, who's the VP of Marketing and Sales, and Mehdi have been instrumental in helping to respond to these RFIs. And I think what our intent is to bring this discussion to the OCP and to all the community companies who are involved in the OCP, and to allow them to respond back to what it is we've put out as a proposal, as a design, as a submission of what we believe the right way is, because there has not been anything like this in OCP to date. And I think at the end of the day, what we're trying to do is really articulate that now is the time to bring WDM into the data center, because we believe that the economics are at a point in time when they will enable that to happen. And I'm really talking 2016. Anything you want to add to that?
No, that's good.
Actually, the economics is part of it. I don't know if anyone else has a question. Let me not. Anyone else have questions on this? I have a question about the economics. Oh, another question? You already asked that? Okay. So the economics, like, so in terms of, I don't know what you can really comment on, but, you know, cost per gigabit in terms of, you know, you look at the 10 and the 40 gig, you know, where we're at right now, cost per gigabit. And if you look at the cost curves, the 100 gig is way up high. And, you know, I mean, my perception of some of the photonic stuff was that it was, especially 1550 based stuff, was pretty high. So if you can comment on, like, when are we going to get to the similar, you know,
that is
possible?
Yeah, so, yeah, I'd like to make a couple of comments here, and this has been really the precise reason that we wanted to bring it to OCP. If you look at 10 gig, 40 gig, and 100 gig, the single mode solutions are an order of magnitude or more expensive than VCSEL and the data center solutions. And part of what we're trying to do with silicon photonics is to bring solutions that are cost effective and that can get the price per gigabit into the VCSEL category. At Mellanox, as Mehdi showed the example, the active optical cable is traditionally a VCSEL application. We are tackling it from the beginning because it's a way of demonstrating the capability of using single mode solutions at the price of VCSELs. And the WDM architecture is extremely important because we want an architecture that scales. CWDM is dead-ended at 4 channels. And we, in the data center, want a capability to go from 4 to 8 to 16 to 32 channels and stay within the same platform to use the very same capability manufacturing-wise, but to use the very same capability from a laser perspective, the same capability from a detector perspective, and to integrate the WDM on the chip. It is a capability which is probably not supported by companies that don't have silicon photonics, so it's definitely not yet supported as much by maybe a Finisar or somebody. But it is one which we think in the OCP that we can introduce as a contribution and work around in a more collaborative way than happens in some other institutions like the IEEE, which requires a very traditional approach to optics. So that's kind of what we're trying to do, and we appreciate the support and the feedback, because we think that this is a forum where we come back to time after time with more contributions.
Can you just address the economic sort of equilibrium that you see happening over the next 24 months?
Yeah, so I think we see that the very cheapest way to make a WDM architecture is with silicon photonics, and to have an architecture where the channels are within the same gain spectrum so that we can scale it, so that we can use the same gain elements, the same laser elements, if you will, but scale it many times over. So in the next 24 months, we're going to want to do 400 gig. We're going to want to do 400 gig, the same platform, the same architecture that we do 100 gig. The easiest and the best way to do that is within a platform that we're proposing, which is silicon photonics.
I get the ease in the migration from the single view on SMF, and I think over 100 to 400. The question is is it cost effective now to kind of invest in that, or in terms of the curve coming down, or do I wait for 2 years or something? But maybe it's a little.
That's a chicken and egg issue, because unless you invest in it now, it won't be cost effective, and if you wait for it to be cost effective before you invest, it will never be cost effective. So the optics industry in general has always suffered from this lack of investment. I have a slide which I took it out to explain that exactly. So what really creates cost in a product in this industry is a lot of it is assembly. And as assembly, I mean thermal management, for example, tuning, the need for tuning, the need for trimming the device, manufacturing tolerances are very critical. But in the optics industry, we are still truncating all our distributions. You have to test very heavily, test is very expensive. In order to have a cost-effective solution, we need to address all these issues. And a lot of these, in these cases, is about developing that infrastructure to do that. So taking this process to a CMOS industry that has the capability is key, but also borrowing a lot of the capabilities on the packaging side, for example. But some of these also get solved by scaling. So for example, once you have to wrap around the thermal management around the product, it may not be terribly cost effective at 100 gig, but by the time you have the scale to 400 gig, then the numbers will start to get a lot more attractive. So, so that's why, for example, a CWDM 100 gig doesn't scale. It's because you're designing a dead-end solution that won't scale. Whereas with us, even if we can match the prices at 100 gig for that product, as we go up to 200, 400, 800, the cost is going to drop very rapidly. And certainly there's a path to get to the $1 per gigabit that everybody's talking about. That's certainly key.
All right. I'm back on costs.
Okay.
You get single mode fiber we've been talking about.
Yep.
You get multi-mode fiber.
Certainly.
You get both. We get
Yes,
silicon
yes.
photonics for multi-mode fiber and single mode fiber. If pricing was not an issue, everyone would go single mode right away. But today I can take silicon photonics and build a system where my price per port would be relatively cheaper than using conventional SFP plus or SFP by using, let's say, like Intel silicon photonics as an example. It's multi-mode fiber, it's really cheap. Company like Molex, they use these MXC connector coming from Corning. They use the same connector for single mode and multi-mode fiber. So essentially, as we evolve where it makes sense to use single mode fiber long distance, you still can use the same kind of low cost cheap connector. So I think cost is absolutely key.
You are absolutely right. cost is absolutely key, but let's make sure we separate hype from fiction and hype from reality. It's very easy for someone to go out there go and say, I'm going to have a product based on a new innovative connector, based on new fiber, and as long as you don't have a product, those claims are very easy to make. As soon as you're in the practical, real life of having to have a product and having to sell it, life is suddenly changed. Intel doesn't have a silicon photonic product yet. And as we know, they just announced that it's going to be another year later before they will have a product. We are in the business of selling real products. And what we say, we have to deliver to. We are selling silicon photonics products already. We ship 1 million channels of silicon photonic products a month. So it's critical for us to talk about real things. Now, you're right. Avago doesn't have silicon photonic products either.
All right.
Very few people have real silicon photonic products, and it's easy to make claims, but it's much harder to deliver at the end of the day. But in terms of cost, you're absolutely right. Now, at the end of the day also, proprietary solutions are often not the answer to low cost in the short term. Because a QSFP shell will cost you a couple of dollars. Try if you went for a new shell that is different, it's not QSFP, but much more cheaper and lower, easier to design or make, it's going to cost you $20. Just because somebody out there is making gazillions of QSFP shells, even though it's more difficult to manufacture compared to somebody else who's come up with a brand new design of a shell or a connector. So yes, proprietary solutions are good and we need to work on them. You're right, we need to have connectors that are far less expensive to make, and don't think we haven't talked to people. We are talking to people. But we need investment and we need momentum in this industry. So we need people like you to go out there and stimulate the ecosystem, to get people to invest in these things. Otherwise, we'll never have the solutions we need.
Thank you very much. Thank you. All right. So I think we're all done for today. Thank you all. It's a great kind of, I love hearing kind of the whole down the optics, switches, new chips, new systems, all the way up to the software stack. So we'll see you all. We've got keynotes and exec tracks tomorrow, and then our session starts at 3. No, at 4.
1600.
Starts at 4 o'clock.